Oh, welcome back, everybody, for section 7.3 in our textbook. This is Math 110, Intermediate Algebra, here at Henry Ford College. And we're going to start with the elementary function when we're adding fractions. These are rational expressions, which means fractions with variables in it. And we are going to add fractions or rational expressions when the denominator is the same. So now from the takeoff of our elementary learning, we have something in this example of 2/5 plus 1/5, and the general rule is the denominator stays the same, and we just simply add the numerators. So that is what's going on at the beginning of our section in 7.3. So they've got an example here that I could do, which would be, actually I'm going to do two of them because they're pretty important as far as the operation goes, all right, when we're subtracting in particular. So let's see, I'm going to jump to something like 2y minus 7. 2y over 2y minus 7. And then I'll get rid of that for now. I'm going to put it over here to be subtracting 7 over 2y minus 7. So what happens here is simply the denominators are indeed the same. I can't factor anything out of that. Sometimes we want to do that. It stays the same, and then I'm just going to take care of the top, and I've got 2y minus 7. So if I subtract that, they're unlike terms, of course, so I got 2y minus 7. And so this will end up simplifying to equal 1 in that particular case. Okay. The next one involves a binomial, subtraction of a binomial, which would go something like this. Okay, and here it is. I paused it and wrote it so you didn't have to wait while I'm writing. Okay, so here's the case of this problem. And remember this going forward. This happens often where we're subtracting now. And that's always a little problematic for us. But the basic here is that the denominators are the same, so it remains the same. And then I'm going to subtract these two binomials. Okay, so that means I'm going to distribute the negative 1 here. I'll leave it up here. And I know the 3x squared plus 2x is going to stay the same, so I'm just going to jot it down here. 3x squared plus 2x. And then I'm going to distribute this negative 1 going across. And that gives me negative 10x. I'll write it here. And negative 1 times negative 5 is positive 5. Alright, so there, I distributed it, changed my signs, which invariably happens, and then I'm going to just combine my like terms. So I end up with 3x squared, let's see, 3x squared minus 8x plus 5. Okie doke, and I think that's about it there. Although I'm looking, sometimes we can factor out something. And I'm looking at this, and when can I do that? I'm going to do it here after I add them or subtract them all together. I'm looking at this, and I'm interested to see, could I get an x minus 1 out of this? This is what we have to check for. All right, so let's factor that. And this is going to be 3 times 5 is 15. I'll do the grouping method. 15. And two factors of 15 that equal the negative 8, so that must mean negative 5 and negative 3. So with that, I'm going to rewrite this binomial. I've got 3x squared minus 5x minus 3x plus 5. Got my 4-term polynomial that I group them into two binomials, and factor this. Actually, I could have done it almost back here. So here I've got what? What's going to come out is what here? I'm going to take out an x, and I've got left is 3x minus 5. And over here, I've got a minus 1, and a 3x minus 5 is here. Alright, so here's my two binomials. Now I'm going to bring out the common binomial factor of 3x minus 5. And what's left over is the x minus 1, and that's what I was looking for. So now this is the trinomial up here factored over x minus 1. So it ends up that these cancel out, and I end up with just the 3x minus 5. Okay, what's interesting enough though, after I distributed this way back here, if I would have factored this out at this point in time, what would have happened? Well, I would have had out here, I would have had an x come out, and I've got 3x plus 2. And over here, I've got a minus, and what can come out here is a 5. And what could I put back? 2x minus 1. 10 divided by 5 is 2. Oh, it doesn't quite work that over here. Yep, because I have to wait till I combine everything. Combine everything till I get to this point. Alright, so remember that. You do not want to do this at this point here. That's not the time to do it. You wait till you actually do your combining. Notice that 2x minus 10x is the negative 8x. So you wait till you do your combining and then factor that part at that point in time to see if you got something that matches that denominator. Okay, next problem. Okay, by the way, this is example 4, and it's on page 504. FYI, for your information. Alright, what we want to do in this section here now is concentrate on finding the least common multiple or least common denominator. Since we're working with rational expressions, it'll be the least common denominator. And what we want to do is figure out how can we get these denominators to be the same as one method for finding the LCD. So with a situation like 8 and 22, well, 8 is not a multiple, they're not multiples of each other. And so what I could do is multiply this 8 by 22. And then I could multiply this 22 by 8. And I'm creating these denominators to be the same. So therefore I could say the 22 times the 8 would give me a common factor of what I would have. Well, 8 would give me, that's not right, excuse me. Alright, let's begin this example. This is example 4. And on page 504, if you like to follow along, where it's finding the least common denominator, given these are fractions, and how you want to do this. So what we do in this case here, in all of our cases, we want to do like a comparison between these two denominators. So if I have 8 and 22, what I want to do is do the prime factorization, since that's what our job is, just to find the LCD. Okay, so we need to find the LCD. That's what it's asking for. So what I want to do is the prime factorization of 8, which would be 2 times 2 times 2 times 2. Okay, and that gives you 2 to the third, or I can just leave it as 2 times 2 times 2. When I do the factorization of 22, that's simply 11 times 2. Okay, everything's to prime numbers now. All these are prime. So what I do is I want to compare my results of the prime factorization. So here I've got 3 2's and only 1 2 with the 22. So the 3 2's win. So I can put 2 to the third as well. Okay. Then I want to multiply that to the winner of the 11. The 22 has a 1 11, but the 8 has none. So I'm going to use the 1 11. Okay, and that's all the numbers I have available to me. So that the multiplication answer, or the product, is the answer. So 2 to the third is 8 times 11 is 88. Okay, so that's what we're doing to find the least common denominator. More in an elementary perspective, I could take my two numbers, this 8 and this 22, and skip count. I don't want that. So I could skip count as I go. So it would be kind of like this 8, 16, 24, 32, what's next? 40, 48, 56, and 64, 72, 80, 88. Now, how about one more? 96. The problem with this way is you don't know how far to go. How far do you go before you get a match? Now, when I skip count by 22s, that's going to be 44, 66, and 88. And I stop there because I recognize, oh, I've got an 88 here and an 88 here. So this is the least common multiple or denominator. Least common, smallest number that divides, that these 8 and the 22 divide into. All right, let's see what else we've got here. Okay, in example 5, and when this situation comes up, this kind of simulates the idea of a fraction with numerical values of, if I had like 1 over 7 and 1 over 5. Okay, and sometimes on problems when we don't have any, what would you say, multiples of each other, I can just simply multiply these two denominators. This would be 7 times 5, which is 35. Okay, I can't derive anything. If I skip count by each of them, I'll end up at 35 as well. Okay, but for the sake of our next problem, when I get this situation with binomials, this x plus 2 and x minus 2. Okay, I really can't manipulate that as well, so I can just say that the LCD equals x plus 2 times x minus 2. And this is the LCD. Okay, likewise I could have written this one as 7 times 5. That's what the LCD is, in maybe a factored form. All right, so that's how you handle situations with binomials that have opposite signs. Okay, next in example 6 here, I've got this 3m plus 15, so I can factor that, notice. So if I take out the 3, I've got m plus 5 left. And then here I can just leave this as it is. It's m plus 5 squared. Okay, now I'll do my comparison. So let's see, starting with the 3, I've got one factor of 3 in this number, 6m squared, but none here for the 2. So 3 is one of my factors of the LCD. Next, I've got 1m plus 5 here, but 2 here. So I'm going to use both of these. So that's going to be m plus 5 squared, the greatest number of times that it occurs. Okay, so this is my LCD. When you think about it, both these factors here divide into this denominator evenly. They both divide into it evenly. And that's what we want. Just like we had the 22 and the 22 and the 8, and we said the LCD was 88, and you notice that 8 goes into 88 evenly, and 22 goes into 88 evenly. And again, that's what we're looking for. Okay, next, here we've got this LCD, and what we've got to definitely do is factor this. We've got to factor both of them. All right, let's see what we come up with here. So can't factor that 2 out, so it's 2 times negative 6 is negative 12. My two factors of negative 12 that give me 1 in the middle is going to be 4 and negative 3. 4 times negative 3 is negative 12. 4 minus 3 is 1, and it's positive 1. All right, so I've got my factors. So what do I do next? I rewrite the problem. 2t squared plus 4t minus 3t minus 6. Okay, now I'm going to factor each of these binomials. So a 2t comes out, and what's left is t plus 2. Okay, and now I've got a minus sign here, which will change my sign on the next one. What was that? 3? 3t minus 6, so I'm going to factor out a 3. And what's left is t. Negative 6 divided by negative 3 is positive 2. And then I'm going to end up with 2t minus 3 and t plus 2. My new denominators here, factored. All right, go over to this one. I'm going to factor this trinomial as well. This is a little easier because this lead coefficient is 1. So that translates in my mind to say, I can just set up my parentheses and fill it in. So I got t, they're both positive signs. And my number is going to be what? A 2 in one and a 1 in the other. Okay, now when I compare the two, here's where we're at now. I've got, I'm going to compare this one to this one in finding my LCD. All right, so here I've got 2t minus 3, one of those, none of them over here. So that's going to be one of my answers, 2t minus 3. Then I've got a t plus 2 here, one of them, and 1t plus 2 here. So that means I'm just going to use one of them, like a tie, t plus 2. And finally, I've got a t plus 1 here, but none over here. So that means I use the t plus 1. And this is our LCD. And you wouldn't multiply that together, by the way. You want to use it separately so you can find other binomials that would cancel out. All right, that's example 7. Moving on. Okay, in this section of the section, our new objective here is to writing equivalent rational expressions, and this is taking on the form of when we have, say, using numerical values, something to the tune of 1 over, I'll use what I used earlier, 1 over 5 plus 1 over 7. Okay, in a case like this, what we want to do, I'm changing this to a problem now so it's more understandable for you. Okay, so what I want to do is, my goal is to get the denominators to be the same. In order to do that, what would I have to do? Well, one strategy is I could multiply this denominator by 7 and this denominator by 5. Okay, however, and a big however, I don't want to just multiply the denominator by itself by 7, because that would change the problem to be 1 over 35 plus 1 over 35. See, it's really not that. It's 1 over 5 plus 1 over 7, which is not equal at that point. So what I have to do is do what is equivalent of multiplying this 1/5 by 1. And an alternate form of 1 would be, in fraction form, 7 over 7. So now I can multiply, I'll have to multiply the top and bottom by 7s. Okay, which I'm really multiplying by 1, so I don't change the problem, the number itself. And with this 1 over 7, I'm going to multiply this top and bottom by 1, or this fraction by 1, so it doesn't change, but I'm doing it in the form of 5 over 5, because 5 over 5 equals 1. So now this problem becomes 7 over 35 plus 5 over 35. And now they're equal rational expressions. Equivalent, I should say, rational expressions. All right, so there I'd have it. So my answer to this would be 12 over 35. All right, so we're doing the same thing using rational expressions with the variables involved. A little bit tricky, but it's definitely manageable. All right, let's go through some examples here of that. All right, here we are, example 9a, and this is our job, is to find an equivalent expression and to create how these are equivalent. So what I have to do here is basically manipulate this 9a so it looks like 27a squared b. So what would I have to multiply that by? So it looks like I would multiply this 9a by, well, 27 divided by 9 is 3. I'd give it another a and a b. Right? And what I do to the top, or to the bottom, I have to do to the top. So I'd have to multiply this to be 3ab. Top and bottom. Okay, we're good with that. And now what will this end up being over here is the 3 times 4 is 12. AB times b is ab squared. And that would be over this 27a squared b, because that's what this is here. 3 times 9 is 27, just to confirm it. A times a is a squared, and the b comes along for the ride. So these match, and I'm multiplying my numerators, and I'm good. This is my equivalent expression. Okay, on this problem, I've got, how can I get these denominators to be the same? What do I multiply what by? Well, it looks like if I factor this out here, I can factor out a 3, and I've got 2x plus 5 left over. Okay, another way of doing that. So it looks like I just have to multiply this 2x plus 5 by 3 to get it to be the same as this, what the fraction on the denominator on the right. So if I multiply this by 3 in the denominator, I also have to multiply 3 in the numerator. So this becomes 21x over, this is okay, I guess, same thing, it's the same expression. Okay, so that's what we've got. That's it. So you could write it as, this could be 21x over the 3 times 2x plus 5. But as you can see, it's this is the equivalent expression here, so you could have written it that way too as well. All right, in our example 10, our last example, looks a little intimidating here, this problem, but it's really not, as long as we know that x squared minus 4 is factorable. That is our key part there, or what that x minus 2 times x plus 2 equals x squared minus 4. So there's a give and take there. So I'll look at this and say, well, I can factor that. All right, so this denominator factors to be x minus 2 times x plus 2. Okay, that's that difference of two squares. So some of our learning from Algebra 1 or beginning algebra is coming back, that part of factoring. And actually we covered it at the beginning of this class. Okay, so here's what I've got now. This is my new denominator, and here's the other denominator. So what do you have to do to make them the same? The denominator is the same. I think I'll do it like this. X plus 2, and then x minus 4. Okay. So it looks like I'm just missing the x minus 4. If I have an x minus 4 here, oh, what am I doing? Whoop. Do it that way. X minus 4 here, now the denominators are the same. But if I multiply this to the denominator, I have to multiply the top by x minus 4. Numerator, denominator. So now I know these are the same. So if I'm multiplying a binomial times a integer, I'm going to do the distributive property, and that would give me 5x minus 20. And now this is my answer. Okay, not bad. And that's the last example for section 7.3. All right, see you next time around.